So let's start with what we already talked about in the lab classes last week. Again, really quickly. So, packet delivery. I'm going to insist again because this is important that you are really aware of how this occurs and you have this well systematized. So, some application sends network data to send. We need to go through all the layers, so usually everything is, we need to have our IP address. Without IP address, we can't send anything to the network. So we need to have our own IP address, and then we receive a packet from the application network with a destination IP address. Okay, so then this is placed on a transport protocol packet, either VTP or TCP, and then this arrives to the network layer. Okay, in the network layer, the UDP or TCP packet is placed inside an IP packet, and that IP packet will have a source IP address, which is the IP address of my machine, and a destination IP address, which is the destination IP of the application layer sent me. Okay, so now I need to get this IP packet and place it inside a layer 2 frame. Okay, and finally, with the layer 2 frame, I can go to the physical layer and send the information through the link. So if I need to place the IP packet inside of an Ethernet frame, I need to know the addresses that I have to place on this Ethernet frame. Okay? So the first step that I need is, if I want to place this IP address inside a frame, I need to know the layer 2 address of the destination. To do this, I will use the ARP protocol. Okay, so this ARP protocol will find out what is the MAC address that corresponds to this destination IP. Okay, so I'm going to do the ARP mapping. I'm going to first see if I already know, because I might have done this before, and the computer stores this in cache. Okay. If you want to check, you can do a simple command in your PCs on the terminal. If you do the command ARP -A for all, you will see a list of MAC addresses mapped to IP addresses that you already have. Typically, you will have at least the gateway that we have talked about in the lab class. Okay? Because usually we communicate to outside of our network. That's why usually the ARP table most of the times has the gateway and almost nothing else. But if we are talking to our network, then I'm trying to solve the destination IP address. That's the case there. I have two IPs of the same network. Okay? If this is a /24, if that's a /24 mask, then every IP starting with 192, 168.3 is from the same network. So if that's the case there, so I'm in the same network, I'm going to try and solve the destination IP. Okay? So I'm going to place this inside a frame, and that frame has to reach all hosts of that network. So that frame will have a destination address, which is the broadcast address. Okay, so all F's. Destination address will be FF, FFF, FF, FF, and so on. Okay, all F's. Why? An address with all the bits at 1 is a broadcast address. In IP, it's the same thing. An address with all the host bits at 1 is the broadcast address of a network. Okay, but in the case of the IP, it's not the whole address. it's the network, it's the host part. For example, in this network here that we have, the 192.168.3.1. So if this is a /24, this means that this is the network part. So the broadcast address would be all ones in the host, meaning that is the .255. Okay. So this is a broadcast frame. When a broadcast frame arrives in a port of a switch, the behavior of the switch is to send through every other port except the one, except the in port where the frame arrives. So in this case it will send through here, but if it had more ports, it would send, if it had another port here, it will send by here, if it had another port here, it will send. Okay, so through all other ports except the one where the frame arrived. Okay, and this will eventually reach the final destination because the target IP is in the same network. Okay, if it wasn't on the same network, on the same IP network, that meant that the host, the final host, was on a different broadcast domain, and if it is on a different broadcast domain, this frame might not reach it, or it will not reach it. Okay, but in this case, first case that we are seeing, it reaches the final destination. Another thing that already happens here is that this switch, imagine that this is port 1. Okay, if this is port 1, this switch already learns that this source MAC is reachable via this port. Okay, so this mapping is done. Okay, this MAC address is mapped to port 1. Okay, because I already received here a frame where this was the destination address. So if this was the destination address and this arrived through port 1, this means that I can reach that address through port 1. Okay, so this reaches the other side, and this host here will see that the target IP that this ARP request is trying to resolve, it's his IP. Okay, so it's going to answer, and it's going to answer with an ARP reply. So it receives the ARP request and it's going to send an ARP reply. Okay, so that's another packet from the ARP protocol, and this ARP reply is no longer a broadcast. Okay, this ARP reply will be sent to the destination address that was the source address of the request. Okay, so another thing that already happens here is that in this reverse path, the switch also knows that on port 2, the one on this side, okay, I can reach this MAC address. Okay, so a mapping for is done here. Okay, this, you see, if I receive a frame here from this source MAC, then I know that to reach this MAC address I have to send frames through port 2. So usually the switches, when in the process of the ARP resolution, already do learning. Okay, because these are layer 2 frames, the switches don't know what is inside, they just look to the Ethernet headers, so they don't know if it's an IP packet or it's an ARP packet. Either way, the behavior is always the same. Whenever they receive a frame, they learn that the source address of that frame can be reached through that port, and they store this in the MAC table. Okay. Then the ARP reply will arrive the host that was trying to do the resolution, and finally I'm ready to send the packet. Okay. So I'm ready to send the packet, and what am I going to do? I'm going to place the UDP packet inside an IP packet with the destination and source, and inside the frame. And I already know the addresses of the frame. So the source MAC will be my MAC, and the destination MAC will be the MAC that I got from the ARP protocol. Okay? Now I'm going to send this to the switch. If this was the first time that this switch saw this destination MAC, what he would do was the same thing as if it was a broadcast. He would flood it to all the ports except the one in which it arrives. But since he already saw a frame with this MAC address as a source, when he received the ARP reply, he already knows that this MAC address is via port 2, because he learned this in this step here. When he received this ARP reply with this source MAC address, he did this mapping. Port 2 can reach this MAC address. So now when it receives a frame in where that MAC address is now the destination, he already knows that he can reach it through port 2. So this is the MAC learning process of a bridge or a switch. Okay, so the ARP resolution part has the added side effect, if you want, of providing MAC learning through the switches along the way. Because there are frames that are going by those switches during the resolution process. So, this is I'm trying to resolve the IP address of a host in the same network. If the host, the final destination, is outside of the network, the process is the same with a difference. Okay, so if in the beginning this IP was, for example, a public IP. I'm going to use here on the faculty we have a public IP starting with 193. So this is a public IP even. This one probably doesn't exist, but no problem. Imagine that the destination IP is this. So this, if my IP is 192.168.3.1, this means /24. This means that this IP is not from my network. So there is no point on me trying to solve with the ARP with this target IP. Okay? Because as we have saw in the lab classes last week, a broadcast domain, a layer 2 zone, corresponds to an IP subnet. So in that broadcast zone, there are only hosts with IPs in the same network as me. Okay? So what the host will do is, instead of trying to solve this IP address, he will try to solve the address of the gateway. Okay? So a host always has to have its IP address, which in this case is the 192.168.3.1, and it has to have a gateway address. Okay? And that gateway has to be on the same IP subnetwork. So the gateway address has to be something. So if my IP address is this, then the gateway, if it's this with a /24 mask, then the gateway will also have to have an IP address that starts with these 3 octets. Okay? So it will be an address like this, with some value here for the host. Imagine, for example, that is the 224. Usually, the gateways are either the .1 or the .254. For example, in our house operators, usually the router that we have at home is the .1, the gateway, and then he gives IP addresses starting in 2, 3, 4, 5, and so on. And they usually use a /24 network because it's the simplest one. And usually we don't have more than 252 hosts at home connected to the router. So it will be an address. In this case, it isn't the .1 because the .1 is the one in the host, so it's something else. Let's imagine it is the 254. This means that this is the IP that the host will try to solve using ARP. This means what? This means that this is an IP of some equipment that is able to do routing, and this equipment must have an interface on my network, meaning that that interface must be reachable using layer 2. Okay. So this means that that equipment is on the same broadcast domain as I am, in the same LAN or VLAN, in the same IP subnet. So these are the two situations. Either I'm going to a final IP that is on my network and I do a resolution for the final IP, or the destination IP is outside of my network and I do a resolution for the gateway. Okay. Third case, I already did a resolution previously and I have that stored in my ARP table of the host, and I don't need, in that case, I don't need to do the ARP request. So we have saw here that, for example, in ARP we have broadcast. Also, even an unknown unicast frame, which is a frame that has a unicast destination, but that the switch doesn't know in each port it is, because he never saw, the switch never saw that MAC address before. Okay? He never received the frame before with that MAC address as the source address. So in both cases, either unknown unicast or broadcast, the switch will flood the frame through all ports. Okay? So this is a problem whenever I have loops. It causes something called the broadcast storm that very quickly fills up the links. Okay? We might think it's a very small frame, but the frame will replicate until it pushes the links to 100% of utilization, and we have nothing happens. Okay? And the network is completely congested. So another problem that loops can cause, besides the broadcast storm, is multiple frame copies arriving at the same switch, which will result in what? MAC table inconsistency. Because I will receive a frame with the MAC address A as source address, and I'm going to map it to port 3, which was where it arrived. And then I receive another frame with the same source MAC address in port 4, and I change to 4, you see? So it's flipping around. That's another problem. I can receive multiple unicast frames on different ports on the switch, and then causes the switch to have inconsistencies on the MAC table because he's changing the matrix between the MACs in the ports. Okay, so bottom line, we cannot have loops on layer 2 topologies. How is this going to be solved? There's a protocol. There's more advanced protocols nowadays, but in campus networks, usually it's still spanning tree that is working, because usually when we buy a switch, it brings some version of SDP running. Even that small switches that are configurable, very small switches that we can buy with like 5 or 6 ports, they run spanning tree. Okay? Because you could connect that in a form that you can make a loop and you will kill the network. So even those very small runs that have all ports in the same VLAN and use some version of STP are working like that. So if we have a single broadcast domain, that's not very good. Okay, imagine a network like that of the figure. Somebody does an ARP here. Okay, to reach the gateway, imagine that the gateway is here. So this interface is also, although it is on a router, this interface has a MAC address. Okay, and this interface also has an IP, and this IP can be of the same network of all IPs here, because this is all on the same broadcast domain, all on the same LAN. Okay, so this is not very good in terms of efficiency, because if this host is trying to solve the MAC address of the gateway, it will send a broadcast, and this broadcast will do this, but it will also come here, it will also come here, it will also come here. Okay, so everybody receives this ARP request, and you are filling these links here, for example, with traffic for nothing, because you only want to reach the gateway. Okay, so it's not good to have a very large broadcast domain. Okay, so we had the VLAN standard, which is the 102.1q standard, that was developed to do just this. If I have a very large layer 2 network with lots of switches, I can use VLANs to reduce the broadcast domains. So what happens is, I can have, in the previous case, I could have here different VLANs. For example, I could have, in this case, this can't be the gateway. The gateway has to be here. So I can have one VLAN here, for example, and this interface is still on this VLAN, and it's the gateway for this one, and I can have one here, I can have another VLAN here, and I can have another VLAN here. What's the difference? Same scenario. If I'm trying to solve my gateway, which is now this device here, okay, then the ARP only goes through here, because when it arrives at this port, this switch receives, oh, this is a broadcast frame, so I must send it through all ports, but through all ports of the same VLAN. Okay, and this port is not on the same VLAN, and this port is not on the same VLAN, and this port is not on the same VLAN. Okay, so it receives an FF here, it doesn't send anywhere else. Okay, same thing for the other branches. So this, of course, improves overall performance, because there are less copies of frames around. Okay, and only the ports on the same VLAN, share broadcasts. Okay, and a VLAN can span multiple physical LAN segments. Now, there is a choice that we can make. A VLAN can span multiple switches, or it can exist on a single switch. Okay? If it exists on a single switch, this has a lot of advantages. So when this is possible, it's the preferred situation. Why? Because if it is on a single switch, there is no loops. So I don't need to run STP. First advantage. Then it is very contained. The broadcast domain are only the hosts that are connected to the same switch. So a broadcast frame that goes here only goes to these ports here.
One host can belong to more than one VLAN?
No. A host has its own subnet, therefore it has to belong to one VLAN only. It can belong to two VLANs if it has two interfaces. Okay? But if it has two interfaces, then the software that runs on the host must be able to deal with that. Okay. Usually when we have two interfaces, if we are talking on an operational system of a computer, only one of them is being used at the time. Even if you have the two IPs in communicating, he's probably just using one of them. But if you have Linux, for example, you can configure Linux to do routing between the two interfaces, for example, and NAT and everything. Okay, so this we already saw in the labs last week and here. So from this behavior of ARP, the first thing that follows is that every VLAN, every broadcast domain corresponds to an IP subnet. Okay, and this has to do with that ARP behavior, because I'm always trying to solve an IP of my subnet. Okay? If that's the destination IP is from my network, I try to solve that IP. If it is not, I try to solve an IP of my network, which is the gateway. Okay? So I never try to solve an IP outside of my network. And since this works like this implies that each broadcast domain has to have its own IP subnet, its own IP network, because that's how hosts know if they can send arts or not. So what we do is that if we have, for example, departments that we want to separate, we can do this. In this case, for example, there isn't any department that exists on more than one building. So we could easily use a VLAN per switch here. So we can, for example, do a VLAN 2 for IT, and this is a switch on building A, VLAN 3 for human resources, also a different switch on the same building but a different switch, okay, and so on. Or maybe these two must share the same switch, and in this case I can create both VLANs on the same switch. That's not a problem also. Only if I had, for example, IT on building A and IT also on building C, and if I want to have everybody on IT on the same VLAN, then that VLAN must exist on two different switches, because they are in different physical places. Okay. Okay, so for example, I can do VLAN 11 and 12, and then do a subnet .11 for 11, .12 for 12, and then I can use 2.1 for 21, 2.2 for 22. So each VLAN corresponds to its own subnet address. You will have to do that on your lab project. You have those VLANs 1, 2, 3, 4, and 5. You have to select subnets for each of them. I don't know the prefix that I gave you for you to subdivide, but I don't know exactly, but imagine that it is like 10.1.0.0/8. So this means that every address on your network will start with 10.1, but now you can use bigger masks to divide this in several networks. For example, you can use that 10.1.1 for VLAN 1/24. You can use 10.1.2 for VLAN 2 also /24, and so on. You should use contiguous networks for the VLANs that are on the same physical side of the network, because later when we do routing, that will be useful for us to summarize the networks into a bigger prefix. Okay, so this was what we saw in the first class, a typical structure of an enterprise or campus network. So both terms are used. If you go into the job market and you're going to work on these things, the the three main, four actually, the four main branches for vendors into which they divide material. Actually, there could be five, but okay. It's campus networks or enterprise networks. Both denominations are used. Service provider networks, core IP networks, which are high-end routers basically, and then the fifth is Wi-Fi and RAN things. Okay, so mobile and wireless networks. And usually there are vendors that specialize. For example, Cisco is not very specialized in mobile things. For example, Ericsson and Huawei are much bigger players in wireless equipments than, for example, in campus networks equipments. And for example, you have, in core IP transport, Juniper is a vendor that's bigger than Cisco historically. So in high-end routers, although Cisco also sells. Cisco is the dominant one on campus networks and enterprise. It's also one of the biggest in data center networks. And in service provider, there's a lot more competition. So in a campus network, this is hierarchical, okay? And now we can have two scenarios, okay? So one of them is two reasons only. I can have layer 2 up to here, but this is only justified if hosts of the same VLAN must exist in two different switches. Okay, because if I have, for example, VLAN 2 here, and I also have hosts of VLAN 2 here, this means what? This means that a broadcast from here must be able to reach these hosts here. So this means that it has to traverse these links. And this means that these links must be on layer 2. Okay, so this is one reason for these links to be on layer 2. If I have one VLAN that spans more than one switch. But if that's not the case, then I could have these links on layer 3. Another hypothesis for this being layer 2 is that these devices don't support layer 3. So there are cheaper switches that don't do routing, okay? And if that's the material that I have, which might happen because the smallest switches that can exist in an enterprise or whatever network might not support routing. And if they don't support routing, then there's no choice. This has to be layer 2. These symbols are different, okay? In Cisco, this symbol is for a layer 2 switch, meaning that this switch doesn't support layer 3, doesn't support routing. This symbol is what they call a multi-layer switch. These are particular names because in tradition, a layer 2 device is a switch, a layer 3 device is a router. Okay? But what happens is that there are devices that are both switches and routers. So they could have called them multi-layer routers, but they call them multi-layer switches. Okay? It is absolutely correct in neither of cases. But there has to be some way of referring to them, so the term that's used usually is multi-layer switch. A multi-layer switch is a device that can have ports that are operating like has a switch, meaning that they do MAC learning, they do flooding, or they work in a broadcast way, and they have ports that are routed, meaning that they have IPs and that they look at an IP table, a routing table, to decide what to do with the traffic that arrives at these ports. Okay, this is another figure that talks about of the same thing. So this is the first case, end-to-end VLANs. Okay, this happens when the same VLAN exists on more than one switch. And then we have local VLANs, where a VLAN only exists on one switch. This is better in campus networks, okay, because layer 2 is more simple to configure, but due to its plug-and-play nature, is also harder to debug and to predict, okay? And it is not so efficient because of spanning tree that only optimizes the paths to the route of the tree, and the route is the same for everybody. While in a routing protocol, each node makes its own tree with himself as the root node. This means that in routing, I'm always going to use the shortest path to any other node, and while when I'm using layer 3, that layer 2, that isn't true. I'm going to use the shortest path to the root of the spanning tree, but not to the other nodes. Reasons to have end-to-end VLANs. In data centers, we saw in the first class, we have virtual machines that are moving between physical servers. And if a virtual machine moves from a physical server to a physical server that is on a different VLAN, that implies that the IP address has to change. Now imagine that if that virtual machine is a web server, for example. Okay? And there is a load balancer that has a public IP address and then translates to another IP address of one of the replicas of the different VMs that might exist. I'm scaling that up because I'm getting a lot of requests. I'm creating another VM and putting in a different server. If I have to if all of them can have the same IP, it might be easier for the load balancer because it can only use ports and it can always put the same IP in every packet. If I change an IP, I have to change the load balancer. Okay? Or it might be even something where there isn't a load balancer. It might be a VM that is doing computation. But now this server is getting very, very full, and the CPU is getting full, and I'm having drops in the performance. So the cloud management software decides to move that VM to another physical server for better performance. And if I change the IP address, everybody that is connected to that virtual machine, or every process that is doing something there, will have a break connection because the IP address changed. Okay, so in data centers, it's good to have end-to-end VLANs because I can move VMs from one side to another, maintaining the IP address. In campus networks, that's not a problem. The only reason that might be good to have end-to-end VLANs is in terms of security, because since broadcasts are isolated, okay, actually, even those, for example, we have those protocols that Windows uses that shows the network computers around us, if they are sharing some directories. It only shows us the ones that are on the same VLAN as us, because that protocol uses broadcasts, okay, and uses layer 2 broadcasts. Okay, that I don't remember. I think there's a protocol called LDAP that's used for that. That is a layer 2 protocol, meaning that it goes inside an Ethernet frame with an FFF. It's a broadcast that reaches every computer on that segment, on that broadcast domain, and only those appear. So, for example, if I don't want to have computers accessible using those types of protocols, I might want to have them all in a different VLAN, and so For example, I want to have the computers of the human resources people all in the same VLAN so that nobody else can see them in this kind of protocols. They need the people from the human resources don't work all in the same room. Then I'll probably need to have that VLAN with more than one switch. So only in this kind of specific scenarios is that this would be a need. Otherwise, we will always try to have local VLANs. Okay. Cores, I need to have devices that support routing. So that would be an issue because they can be more expensive. Okay. Nowadays, not so much because almost all of them support routing. For example, we have at homes, at our homes a multi-layer switch. The router that we have at home is Ethernet in the Wi-Fi part and in the LAN ports, because usually they also have wired LAN ports, where they work at layer 3, and then they have a one interface with an IP, and they do routing and NAT, and they are cheap devices. Most of the time they are very cheap. That's a problem. That's why they aren't very good. Okay, so configuration, you already seen this in the labs. Creating a VLAN, the command is VLAN and then space and the number of the VLAN. You can give a name to the VLAN, then you exit the VLAN configuration mode. Then you need to go to the interfaces and say that they belong to a given a given VLAN. Okay, so in this case, I'm going to this interface. I am telling it that is a switch port in mode access and that it belongs to VLAN 3. Okay, we have the same thing here. Create VLAN 99, give it a name. This is not needed. You can, okay. You can also, inside the VLAN configuration mode, you see here, before you do the exit command, while you are still in the config VLAN mode, you can list interfaces here, and these interfaces will be on access mode VLAN, in this case VLAN 99. Okay, so this is an alternative to this. You can create a VLAN, then go to the interface and do this, or you can create a VLAN and inside the VLAN configuration mode already put an interface, and this interface will be on mode access on that VLAN. Okay. In this case is the same thing that is on the other way. So in this case we have 15 and 16 both belonging to VLAN 99. Verification you can do on the enabled, on the privilege mode, show VLANs. It shows the created VLANs and the ports that are on those VLANs. Here the ports that are on mode access will appear, but also the trunks. Okay, what is a trunk? A trunk is the mode in which I have to place a port where more than one VLAN must pass. Okay, so usually the ports that are connected to hosts only have one VLAN, which is the VLAN of the host. Okay, that's why they are called access ports, because they are the ports where the host connects. Or it can be a port where Wi-Fi access point is connected, if all hosts in that Wi-Fi access point are on the same VLAN, for example. Okay? But the links between switches might need to transport more than one VLAN. Because if I'm talking about an end-to-end VLAN situation, I have VLANs on multiple switches, and the traffic must traverse the links between the switches, and there might be more than one VLAN passing in those links. So when the frame arrives at the port, the switch has to have a way to know to which VLAN it belongs. Because it does switching, but it only does switching between the ports of the same VLAN. So when a frame arrives on a link where more than one VLAN can exist, I need to have a way to know if that frame is from VLAN 2 or 3 or 4 or whatever, so that I know to which ports I need to send that frame, if it is a broadcast or an unknown unicast. Or even if it is a known unicast, I also know that I have to send to the port that I have on the MAC table, and that port must belong to that VLAN. Actually, the switch has a different MAC table per VLAN. So, the Ethernet frame needs to have a field where to identify which VLAN that frame belongs to. It's called the VLAN tag or the VLAN ID, and this was defined on the 102.1q frame standard, okay, and it's called the 102.1q frame. Okay. And it sits here after the intertype. The intertype we also saw in the first class is a field that tells what's inside of the Ethernet frame. If it is an IP packet, if it is an ARP packet, if it is a DHCP packet. Okay? Usually it's one of these three. It can be an LDAP packet also, which is the one that Windows uses to discover the nearby computers on the same network. There's also another layer 2 protocol that you might see, which is LVP, which is sent by switches themselves to try and discover the topology and see if there is somebody connected on the other side. So there are several layer 2 protocols, and that field tells us which of these protocols is being transported on the Internet frame. Okay? So, a 100.1q link is called a trunk, and it has that field because there can be several VLANs passing here. So, there's a special VLAN which is called the native VLAN that doesn't transport the tag. Why? It's by elimination, of course. Okay? So, if it doesn't has a tag, it's from the native VLAN. If it has a tag, it's from the value that is in the tag. So for example here, VLAN 1 is not tagged. So here the frames arrive without any tag because only VLAN 2 exists in these ports. It goes here with the VLAN 2 tag. Same thing here, VLAN 3 tag. VLAN 1 is not tagged, so when a frame arrives here, the switch knows if it doesn't have a tag, it knows that it's from VLAN 1. It's from the native VLAN. If it has a tag, it looks at the tag to see to which ports it needs to be sent. Okay, configuration of trunks. We already saw this also in the labs. So this is creating the VLANs. It's not related with the trunks themselves. Okay. Then I go to the interface that I want to configure as a trunk. Okay. I'm going to the interface that I want to configure as a trunk. In this case, it's fast Ethernet 01. Shut it down. Encapsulation.1q, non-negotiate, mode trunk. Then this is optional. If I want to change the native VLAN, by default is 1. So if I don't do this command here, the native VLAN will be the VLAN 1. This is if I want to change to another VLAN. And then I have to say which are the allowed VLANs. What this does is, when I do this command here, I'm saying that this port belongs to VLAN 3, VLAN 5, VLAN 8, and VLAN 99. You see? It belongs to all of those VLANs. So when you do the show VLAN command, they will appear, the same port can appear on more than one VLAN if it is a trunk. Okay, then the no shutdown. What's this non-negotiate? So this is a Cisco thing, okay? There is a protocol called dynamic trunking protocol, okay? And by default, I think usually Cisco switches are on this mode, dynamic auto, okay? So when we connect both, if we connect a switch without configuring anything, we connect a link between two switches, the port will be in access mode automatically because it's a dynamic auto port with a dynamic auto port, and this VTP protocol will make them access, which is not something that we want, because usually a link between two switches is not an access port. Okay, an access port is to connect to a switch. Okay, if it's a dynamic auto with dynamic desirable, it's trunk. Actually, I don't know if it's not dynamic desirable that they are by default, but this this probably varies between firmware versions. Okay. Okay, and then we have trunk manually with that no negotiate command. Okay. And what we want is these yellow ones, which is no negotiate on one side and no negotiate on the other side, and have a trunk. Sometimes you have problems in the project because you configure one and the other one is in dynamic auto. And for instance, what could happen usually, if this one is trunk, even if the other one is dynamic auto and dynamic desirable, they will be in trunks. So if it's just one link, it will be okay. But when we are when we bundle them in EtherChannels, remember we talked about in the practical classes, we will see next. So we will want to bundle more than one port, and then the confusion begins, because if it's only one side that is trunk, then not all ports will be trunk on the other side, and sometimes he gives a warning saying that trunk is incompatible with dynamic auto. It will say the port is already in dynamic auto. So that's why I told you when you are doing EtherChannels that you should configure with the range both interfaces at the same time, and tell them at the same time that they belong to a port channel, and do the same thing on the other side. Also, VTP. VTP stands for VLAN tracking protocol. So this is a protocol that was used when end-to-end VLANs were more common, because Ethernet is very old, okay? So it's about 40 years or something already. And in the beginning there was a lot of traffic. So Ethernet precedes the internet, okay? So there were already Ethernet networks on campuses, while the internet was still in its infancy and only connected a few colleges in the United States and so on. So there was a lot of traffic between hosts on the same Ethernet, and it was most common to have larger VLANs. Then, as the internet started to grow, the traffic shifted from east-west. It's what we call, when the traffic is between hosts at the same network, we call that traffic east-west. And it shifted to north-south to south-north, which is when it's from inside one network to outside of the network. Nowadays, 99% of the traffic in a campus network is north-south, okay? It's to outside of the network. Even if it's not to the internet, because in companies it's very common to have a lot of traffic to servers that they have in data centers, okay? But even so, most of the traffic is, the data center is not in the same network also. Okay, so this VTP comes from that place where end-to-end VLANs were more common, and the idea was, okay, I don't need to configure the VLANs in all the switches where the VLAN exists. I can use a protocol where I configure just on this one, and then the configuration propagates to the others. Okay, so this protocol could be used in this server mode. I configure all them in the same domain, with the command VTP domain. Then this one, I say that is a server, and these ones are configured like clients. If I want to create a VLAN in all of them, I just needed to create it here. Okay, and that info will be propagated using the VTP protocol. Okay, so this is a server and a client. Then we have the transparent mode. The transparent mode means that the switch ignores VTP messages. Okay. So we could use VTP and dynamic auto, and if we create the VLANs here, if this is on dynamic auto, this would automatically be trunks, and the trunks would allow all the VLANs that exist on the switch. Okay, but it can prune some of them. For example, here it can prune VLAN 3 from here, because although if we use VTP, VLAN 3, all the VLANs will exist in every spot. Okay, if we use VTP and this is the server, I will create VLAN 1, VLAN 2 and VLAN 3 in all switches. But as we see, VLAN 1 exists here and here, and VLAN 2 exists here and here, and VLAN 3 here and here. So it's an end-to-end situation, and probably I do want the VLANs to exist everywhere because of redundancy. But if we see here, even if there are some alternative paths here, they won't be used because VTP, for example, here will see that VLAN 1 and VLAN 2 are never sending here broadcast traffic, so it will cut the broadcasts of VLAN 3 here. So usually, if you're going to, even if you're going to study for a Cisco certification, this is there. They themselves do not advise on using VTP because it's prone to errors. Because since you are configuring stuff on one switch that is in that configuration is being propagated to other switches, it's easy for you to have some things on switches that you don't want to. Okay, so it's safer to control everything. Okay, so usually the configuration that we are going to do in the lab is place the switches on the transparent mode. The password is not needed. We can also place them all on the same VTP domain, because if they are all in the domain and they are all transparent, nobody is going to send any VTP messages. So you can see if it is disconnected or not doing the command show VTP status. These show commands are all done in the enabled mode, in the privilege mode. Okay, so it tells the version of the VTP. There are two versions, and usually what we need to see is if we have everybody on transparent. Sometimes in labs you forget to do this, and sometimes you have some strange situations, and they have to do with not having this on transparent, having VLANs where you don't think they are, and then spanning tree. You can never forget that spanning tree is always running, and spanning tree will run it will either make the same tree to all VLANs, or by default in Cisco switches it makes a different spanning tree for each VLAN. So you might have a very strange tree configuration because you have more VLAN. The VLAN exists in more places than you want. Okay, so check if you have everything in transparent mode. Okay, so common problems that VTP can cause: missing VLANs because a configuration can be overwritten by another VTP device. So imagine that you want to create a VLAN on one that is a client, and then somebody on the server creates another one. It will erase that one. Okay, because you will always have the same configuration that the server has. So you thought that you created a VLAN on a specific switch and you didn't because of VTP. Okay? So you can also make a mistake on the domain name, for example, and put, for example, you can put a character that is wrong, and you are looking at it and you think they are in the same domain, but you mismatched the character, and you can have the other way around. You think you created the VLAN and you didn't create it because they were in different domains. Okay. Also, if you have a big VTP domain and a server and clients, you can have too many VLANs. You might be creating VLANs in places where they are not needed. Okay, so the recommendation is to not use VTP, okay, and also to not use DTP and disable trunk negotiation. Okay. Verification and troubleshooting of these things. Okay, you can do the show running config. For the show running config, if you don't put this part, will show the entire configuration that you have at that point. If you want to see a specific part, you can add things here. For example, this will show the running config of this interface only. Okay. You can try to see if you have connectivity using ping from one host to the other. If connectivity is not happening, you have to see if they are in the same VLAN. You have to see if the VLAN is created in all of the switches. You have to see if these ports are on access mode and on the correct VLAN. Then you have to see if these trunks are correctly configured and are correctly operating, and if they are allowing VLAN 10 to pass. Okay. You can do this by checking the configuration. On CML, for example, you can do captures of the links, so you can see, like we could see with Wireshark. I think that uses Wireshark. So there's a special protocol called PCAP, and actually is a protocol in the format of a file that captures packets on interfaces. Okay, so this, you can see every packet that goes to a link, and you can see if for example an ARP request, if you try to do this ping, okay, this is a ping for an IP which is of the same network as the host. So the first packet that you will see passing here is the ARP request for this target IP. So you can check links and see if the ARP request is passing here but not here, then there is some problem with this trunk. Because if the ARP request isn't passing here, probably this trunk doesn't allow VLAN 10 or is down, and then the switch doesn't flood the frame to that port because it does not belong to the same VLAN, or because it is down or something like that. Okay, you can check the status of the trunks doing show interfaces trunk. Okay, it will show the trunks that are already created. It will tell if they are up or down, and it will also show it will also show which VLANs are allowed in that trunk. Okay, so common errors that might occur, you have to see if the VLAN was added to all switches. Okay, if it's pruned somewhere, this means if there is a trunk that is not allowing that VLAN. Do you have the correct VLANs in the access ports? Is the port enabled, meaning it might be shut down, because you can do the shutdown command and forget to do the no shutdown command in the end. Okay. Is it a switch port? Is it in the mode access? Okay. The trunks, are the trunks up? Are the VLANs allowed that are supposed to be allowed in the trunks? Is spanning tree blocking one of them, and you have no alternative connection? Okay. So DTP complicates things also. you need to have both links on the same VTP domain. In order for DTP to correctly be used, you need to use VTP without the transparent mode. So we don't want to use DTP also. Okay, so we should use the trunk no negotiate on both sides. So this we already saw. Native VLANs are carried here without the tag. Okay. And usually it's VLAN 1 if you don't say anything in the contrary. Okay, though this is the summary, we already discussed this. So, what did we saw more that you need in the lab? Usually you have a tree, okay? We have saw there that for example in the campus network you have access nodes, and then this connects, for example, to an aggregation node, and then this goes up to a core node. Imagine that you have something like this. Now imagine this is a gigabit interface, and then you have the traffic from two gigabit internet interfaces passing through one link, which is also gigabit. So if these are being used to the maximum, there will be congestion here. Okay, so I need this one to have double the capacity. Otherwise, the network itself can never be completely utilized. The lower links can never be in 100% utilization. I could only have 50% utilization here and 50% utilization here, because here I had a bottleneck. So I have no interfaces with higher than gigabit speeds. What do? I connect two. Okay, but if I connect two in a broadcast domain, this is a problem, because as you see here, these things are loops, and spanning tree will cut one of the links. So I'm back to the drawing board. I can only have 50% on each one, because one of these will be cut, because this forms a loop. Okay? So very early on, a protocol appeared that in order to do what? This to appear to layer 2 has a single link, meaning that spanning tree, for example, sees this has a single link. Okay, this is the idea. So what I need to do is that group these links in order for spanning tree to think that that is a single link. Okay, and this is what? This is using a protocol that will manage the way frames leave those ports, so that there's never a loop. Okay, for each frame it will only leave through one of the ports, and then it will do some kind of loop distribution. You see, but one frame only leaves through one of the ports. Otherwise, I could have a loop problem. So I have a protocol that does that. Okay, that does load balancing between the two links. But when for example, I have a broadcast, that frame only leaves through one of them. Okay. And when it arrives here, for this switch, it is the same as if it has arrived also in here. So in the flooding mechanism itself, it won't send the frame back, because in flooding we never send the frame back through where it came. Okay, so this is called in Cisco terms, it's called an EtherChannel. Okay, it can be done on layer 2, which is what we will see today, but also in layer 3 ports. Okay, I could also group 2 links or more. There might be more than 2. It can be 3, 4. And in case of layer 3, I can group them and they have the same IP, because it's like they are a single one. And also in IP there's load balancing. Usually in IP it works by sending in a round robin way to the links, packet to this destination X goes to this one, then the next packet for a different destination goes to the next one. Okay, so there are two protocols here, LACP and PAGP. Okay, this one is proprietary from Cisco, so it's not a standard. The standard is this one, LACP. Okay. This is the one that is configured by default, okay, by Cisco. This is another protocol that if you are doing captures on the links, you will see in the ones that are grouped. You will see frames there that are transporting LACP, the LACP protocol instead of an IP packet. Okay. You could actually do, this is what we do. We can also do, this is the one that I showed in class, which is the mode on. The mode on doesn't even use protocol because it does not need to communicate anything. What it needs to do is the local switch must know that those two ports are to be seen as a single one. Okay, so this is what we usually use. On, it works. If I have one with off, I don't have an EtherChannel. Then it also works if both are active or one of them is active and the other one is passive. In other years, you're not obligated to do the mode on. Mode active also works. If you put mode active in both sides, also works. The difference is that it is exchanging LACP packets. Okay. Actually, LACP is meant to be used with one active and one passive. But the easiest way to not have problems is to configure with on and configure on both sides equally. Actually, if you do what I advised you to do with the text files, you just have to copy paste and it's exactly the same. It's even easier than placing one in active and the other one in passive, which would mean more configuration. Okay, so this only works if the ports are all of the same speed and duplex mode. Okay, usually all Ethernet ports are full duplex, but to do an EtherChannel, they have to be both gigabit Ethernet or both fast Ethernet. You can bundle a fast Ethernet port with a gigabit Ethernet port, for example. They all have to be on the same mode. That's why on the lab I told you to do that with the range command, so that you can guarantee that all ports that you are bundling have the exact same configuration and are in the exact same mode. Okay? Same native and allowed VLANs if they are a trunk. If there are access ports, same access VLAN on all of them. Okay? This is what I don't advise you to do as it is here. I think it's best to configure these parameters on the links and not configure anything on the port channel. The port channel is the port that is created. Okay? So I don't advise you to do this like this. Okay? In the slides, they go to each of the ports and only do this command. Okay? In our case, it could be on instead of active. Okay, so it goes and does channel group 1 mode on one port or active, channel group 1 mode on the other port, and then this creates the logical port channel. Then I can go to that interface, the port channel 1 interface, and then do the configuration there. From my experience, it works better, it gives less worries if you do the other way around, which is you use the range command. In this case, for example, for these two ports, you would do interface, range, fast Ethernet, I'm just going to place F 02324. Okay, so this command, what it does is it enters in the config interface mode. Okay, but I'm placing commands for both interfaces. That's what the range does. The range is when I need to put configuration which is the same on more than one interface. I can use that. So I would do the trunk configuration, which is this part here, now, here. And then in the end, I would do the channel group. Channel group 1, mode on or active. And that's it. Then now I don't need to go to the port channel and configure anything, because I already have the mode that I want in all of them, and I already told in all of them that they belong to the same channel group. Okay, so in this case there are 2 steps even. I do everything in the interfaces. Okay, in the slides you need to go to the interfaces just to place the command that creates the port channel, and then you would have to go to the interface port channel and do the configuration. So this not only gives less problems, it's also easier because you do everything in one go. Okay, you can also see if everything is working if you do the show interfaces for a given interface. This is F024, which is here, and then EtherChannel. So you have to do this for each port, and it shows for this specific port if it's up, if it's working, okay, which mode it's being used, what is the number of the port channel. Okay, we can also do show EtherChannel 1 port channel. It also shows if it is using a protocol and which ports are bundled here. In this case, the 23 and 24. Can also do show EtherChannel summary, which usually in the lab this one is what you usually do, just to see if the port channel is up and if the ports are correct. Then usually you go and see the trunks, and then the trunk will be associated with the port channel, and if the trunk is up, everything is okay. Okay, so this does load balancing, as I was telling you. It loads traffic among the port members of the same bundle. Okay, if it is a layer 2, it's based on MAC. Okay, if it's on layer 3, it's on the IP. Okay, you can change this also using the port channel load balance type. We usually don't do this, we use the default one. Okay, so EtherChannel is important because of having a way of having more links with more bandwidth, okay, without having loops. By the way, if it was on layer 3, you don't have the loop problem, but it's also easier to have the bundle, because if you have the bundle, you just need one IP address. Actually, in layer 3, you don't gain much aside from not having the burden of having more than one IP and one network, because a routing protocol in that situation will also do load balancing, because the path will be on the same side, of the same size, of the same cost through both links. So if you have on layer 3, this is not a problem because there aren't loops, but the thing is, if you don't use EtherChannel, this has an IP, this has an IP, and this is a network, a subnetwork, and this has an IP, this has an IP, and this has to be a different subnetwork. And that's cumbersome in terms of configuration. And you have to also use more IP addressing space. And also in terms of routing, this will add more routes to the routing table unnecessarily. And we also always want to have the smallest amount of routes in the routing table possible, because the routing matching is a very expensive algorithm, because you have to match the longest prefix. So you don't even stop on the first hit. You have to check the whole table, okay? So that's why EtherChannel in these situations for layer 3 is also very useful, because it will allow us to not have the routing table so big, and apart from that, it will save us the work of having to configure different IP addresses and different networks in all the links. Okay, so now we went a little bit faster because some of this we already had discussed in the lab classes, and that gives us time to advance a little bit on the next class, so that also in the labs you can do a little bit more. Okay.